तीसरा होत नहीं है था, दूसरा है। ठीक है ना, एक तो एनी रिकॉर्ड किया, यू ऑलरेडी रिकॉर्डेड वन सेशन लास्ट टाइम। So, a very good afternoon to all the participants in this online interactive session this afternoon. I hope we know one another by now. I am Gadre. I am a professor in the Department of Electrical Engineering at IIT Bombay, and I happen to be the instructor of this course on digital signal processing and its applications. And I have my young friend here, Aniket Sadashiv, who is the coordinating teaching associate in this course. And you would see that he has also provided you one session, explanatory session in this course. I hope all of you have seen that session. And he has provided a recording of a session which will help you. So that should constitute the third session for you, all of you, because he has taken the trouble to identify certain key points which many people I think find difficult, and he had taken the trouble to make this session available to you by recording it and making it available on the portal. So now, with this little introduction, I am very happy to invite all of you to put forth your questions, and we'd like to answer as many as we can today. Now, is there anyone who would like to pose any question right away online on the live chat? So please do that. But meanwhile, I'll take up one question which I saw. These seem to be somewhat general questions. I saw one question posed by Narendra, I think. Yeah. It was posed by one Narendra. Is Narendra there today? So if he is, then he says, what is the best way to remember this DSP formula? Now, I'm not sure which formula he's talking about, whether he's talking about one specific formula, but my general response to that question is that as far as possible, you must distinguish between what you need to remember and what you need to understand. For example, there is no need to remember all the expressions for the windows for finite impulse response filter design. It's a waste of time. It's not required. You're always welcome to refer to a table which gives you the window expressions, the expressions for the window sequence. You don't have to remember them, except maybe for some very simple windows. Well, I don't know whether are there any others. I think people will join in a short while. So is there anybody in the live session this afternoon? Can you respond in the chat, please? We'll wait for some response. I think there are, there is something here. Not yet. Narendra. So Narendra is here, I guess. So Narendra, are you there? If you're there, please respond in the chat. So could people please respond in the chat, those who have connected right now? Okay, now we have 3 people watching, I notice. So, uh, could we have your questions, please? Could you put it in the chat who is present in the call just now? Could you just share with us in the chat who is present in the call just now? And tell us what questions you have. Is Narendra present in the chat? Looks like Narendra, the one who's asked the question on DSP formulae, is he there in the chat? Yes. So I'm happy to see that Manu Kumar Sharma is there in the chat, and a very good afternoon to you, Manu Kumar Sharma. I hope you can hear me, see both of us. So I'll begin once again to introduce us. We have to keep periodically introducing, I think, because people are joining now and again. So Manu, this is my teaching associate, Aniket Sadashiv. I think you might have interacted with him, or you might have seen the nice video that he's put up as an explanatory session on some of the assignments. And I'm Vikram Gadre, and I'm the instructor, and he's my teaching associate. I'm very happy to have you in this discussion. And now you've asked me, can you explain a little bit about instantaneous sampling, like how delta function is used in sampling? Okay. Now let me explain to you by Let me explain to you by I'm sure you're able to see the whiteboard. You're able to see the whiteboard. And now you see, let's understand what sampling, how sampling practically works. Right? So, this has to be here, no? This has to reflect here. So this evasion is it will come. Okay. All right. So, you see, practically, how do you sample practically, instantaneous? Okay, so practical sampling. Practical sampling happens by multiplying the signal with a pulse train, not an impulse train. An impulse is an idealization. Now, how do you multiply a signal by a pulse train? Next page. So how do you multiply a signal by a pulse train? You essentially pass the signal, that means pass the signal for a short interval and then stop the signal. Then impede or stop the signal. Okay? So essentially, it's something like this. Let me sketch. I have some signal. Let's say it's an audio signal. It's a function of time. You're essentially multiplying it by a function that looks like this. Multiply by so essentially this interval is the sampling time, and this interval is called the hold time. So this is a pulse train, a uniform pulse train. So how would the signal appear when it is multiplied by the pulse train? The signal would look like this. Let me use a different color now. Maybe we'll use orange. So we have this go through, and then the signal falls to 0, and then this, the signal falls to 0 again. This, the signal falls to 0. Let's mark it like this. And so on. So this is what is called natural sampling. This is how typically sampling is done. Okay. Now, how do you actually analyze such natural sampling? So the pulse train is a periodic signal, right? It's a periodic signal with period Ts, and therefore it can be expanded in its Fourier series. Let's write down that Fourier series. Summation k going from minus to plus infinity, ck e raised to the power j 2 pi by ts kt. You're multiplying it by this Fourier series, essentially. This is the Fourier series. It's very easy to obtain the Fourier series of this periodic signal. I leave it to you, right? If you want, I can calculate. In fact, you can calculate. It's not very difficult, right? So how will you obtain ck? Ck would be obtained by 1 by ts integral. So what you can do is you can either place it in the middle, or you can place, or you can just start from 0 to th. Okay, e raised to the power minus j 2 pi by ts times kt dt. So this is, you can calculate this. These are Fourier series coefficients. So e raised to the power of course when k is not 0, from 0 to th. So you could evaluate this, and for k equal to 0 you can see that it's just the integral from 0 to th dt. That's easy to calculate, so it will be th by ts. In other words, you can calculate for k not equal to 0, you have the expression here. For k equal to 0, C0 is simply TH by TS. So these are Fourier series coefficients. Now when you multiply xt by this Fourier series, so what you're doing is you've taken the original band limited signal, hopefully xt is band limited. Xt is multiplied by summation k going from minus to plus infinity, ck e raised to the power j 2 pi by ts kt, and the Fourier transform of this is summation k going from minus to plus infinity ck times, now the Fourier transform of xt multiplied by this exponential is essentially the Fourier transform of x shifted by 2 pi by ts times k. So what does this expression tell us? This expression tells us that for c equal to 0, C0 gives the original spectrum. Normally, it's a band limited baseband signal. And Ck for k not equal to 0 gives the aliases. Now, what we need to appreciate is that the only difference between the idealized form of sampling and natural sampling is that CKs are not all equal. So let me explain that to you. So the CKs are not all equal now. If you have natural sampling where you've kept some part of the signal and then suppressed it every time, then of course the CKs are not all equal, right? Now so essentially the aliases would be of different strengths for different multiples of the sampling frequency. That's the only difference. But all the aliases would still be there. And of course, you have to cancel. So now the same principles hold. The Nyquist theorem holds the sense that the first alias must not overlap over the baseband spectrum and so on and so forth. Now, as you make TH tend towards 0, but then retain the area under that narrow pulse in the beginning of the period, it becomes instantaneous sampling with an idealized pulse, right? Now, what I'll do is I'll stop this explanation here and ask Manu Kumar Sharma whether he understands what I've explained so far and whether he has any further questions in what I've explained so far. I will answer them. But meanwhile, let me take up some questions which I've got from MPB, right? I'll in fact request my teaching associate to look at those. They seem to pertain to the assignments. No. The internet is not working. These people seem to have, chat is coming. Internet is not working. Internet चालत नाही आहे. आत्ता डिस्कनेक्ट झालं का? हो एअरप्लेन. working earlier? It's okay. What point do you notice the impact was not there? Was it something when I was explaining or
When
not?
scrolled up.
Oh. No, this is a. Wait. What are we doing now? Speak into this, is it?
Internet here is working.
Okay. No, but then will our voice go from here? Or the chat will come from here?
Chat will come.
Chat ह्याच्यात येईल का सर? मग ह्याच्यातनं इंटरनेट जाते? Chat. Okay. I'm sorry, there was a problem with the internet. So now, Manu Sharma, I have tried to, I hope you were able to listen to my explanation of the, natural sampling and how natural sampling is different from idealized sampling. Please let us know if you have further questions. Okay, now, so Manu Sharma has been able to hear us. Very nice, Manu. So Manu, are there any further questions that you have on this? And we'll be happy to take them. Meanwhile, as you answer, so Manu, you can tell us if you have further questions. Meanwhile, I'll let Aniket look at the questions on the assignments.
Assignment 6, question 7, that we have noted, that needs a correction, that I'll forward.
So are you able to hear him? What's his name? MPB. Can you hear Aniket? He says that there's a correction in one of the assignments.
If you can respond.
Yeah, so MPB, could you respond to, to say that? So maybe there's one or two corrections are there, so that Aniket will take care of those. But meanwhile, let me take the next question by Bharat Srivastav. MPB, yeah. I regret there is no response from your side on wrong keys and assignments. What do you mean? I think we have been responding to all the questions. If I'm not mistaken, I think we have been responding to all the questions. And I think Aniket has been very conscientious about responding to the questions. And we also regret that many of you, it's a little unfortunate, and I'm not sure who this gentleman or lady is, but it's very unfortunate that some people have been very uncouth in their, I should mention this now that this gentleman is saying this on the chat. I must mention that there have been some people who are very, very rude and very, very uncouth in the way they write, write things to NPTEL. As people who are, I believe, taking up an advanced course, we should be more careful in the language that we use. Now, I'm not saying that there is, this could be a problem in this case, but we have had some, extremely rude, I think, one can write, see, I think in general NPTEL is quite responsive to your concerns. And I think a lot of leeway has been given to, err in the assignments and so on and make up. But it's a pity that some people are not very polite in the way they communicate. That's something that we would like to make it clear on this forum. Anyway, that apart, that's the unpleasant thing. Let's come to a good question which Bharat Srivastav has raised. Is there any method other than the usual formula to calculate the 16-point DFT? Because calculating with formula for DFT takes a bit longer time. See, in general, one must use the recursive expression for the discrete Fourier, for the fast Fourier transform. I think what you are asking is, can you construct the 16-point fast Fourier transform, in an efficient way? If you wish to construct fast Fourier transforms of larger and larger orders, the best way to do it is incrementally. Begin from a 2-point DFT, then use the basic idea of the radix 2 fast Fourier transform, namely a fast Fourier transform of n points is equivalent to 2 if you are doing decimation in time. It's equivalent to 2 fast Fourier transforms of n by 2 points followed by some additional computation, which essentially is the twiddle factors followed by butterflies. So each time you have these twiddle factors and the butterflies giving you the additional computation, and you have the 2 n by 2 point DFTs. Now this is a way to go from a larger number of points to a smaller number of points. But the same idea can be used to go from a smaller number of points to a larger number of points. So you could construct the FFT also like this. So for example, to construct a 16-point FFT, you put 2 8-point FFT blocks. Let me in fact show that with a drawing. Let me show it to you with a drawing. So suppose you want to suppose the 8-point DFT is available, or 8-point FFT is available. Then what do? You take 2 8-point DFTs like this. Now here you put the twiddle factors. On the lower branch you put the twiddle factors of the form e raised to the power minus j 2 pi by 16 times k. K going from 1 to 8, from 0 to 7. And then you use essentially what are 2-point DFTs from the corresponding points here. So we put 8 butterflies here. Which are essentially 2-point DFTs. So thus one can, if you know how to construct an 8-point fast Fourier transform, you can construct a 16-point fast Fourier transform. And we can keep doing this. So in general, when you have an n by 2-point DFT, or FFT, then you can take 2 such and then put the twiddle factors here, and then the butterflies. So n by 2 butterflies. And thus we get an n point FFT. Yeah. So this way we can keep expanding. See, so what I'm saying is this recursive principle can take us both from a larger number of points to a smaller number of points, and also from a smaller number of points to a larger number of points. So you can keep, now the butterfly itself is a 2-point DFT. So you can begin from the butterfly and make it a 4-point DFT. Then you can begin with a 4-point DFT and make it an 8-point DFT. And thus you can go on increasing the number of points. So Bharat, does that pertain to what you wanted in the question? So Bharat, does that pertain to what, does that address your question, Bharat Sharma, Bharat Srivastav? Yeah. Now, while Bharat responds, I'll take up Manu's next question, Manu Sharma's next question. What is the physical significance of the twiddle factor in FFT? How is it used in beam forming for radar to estimate the angle of arrival? Okay. You see, the twiddle factor is essentially, there are two ways to understand it. The twiddle factor is a part of the complex exponential. It's a part of the complex exponential, right? So, one way to understand it is that it changes the phase. So, when you are talking about the angle of arrival or direction of arrival and so on, you see what do? You often combine different beams with different phases. Now, phase shift is reflected as a twiddle factor. So you can think of the twiddle factor as introducing a phase shift. That would be the physical significance. It does not change the magnitude, it only introduces a phase change. And then, you can combine different beams with different phase change factors to add constructively or destructively. I think that's what you're asking, but if you have some further questions, please do put it in the chat. So Bharat Srivastav says that he has been able to understand the answer to his question. And now let me ask Narendra. Is Narendra in the chat? Now Narendra, you have asked us what are the ways to remember DSP formulae, I think. Could you clarify your question a little more? Because we haven't quite picked up which formula you wanted. But let me make some, while you clarify your question in the chat, let me make some general remarks about DSP formulae. You see, I was telling in the session, at the beginning of the session, that one does not really need to remember all the expressions. The idea from this course is not that you should memorize, for example, the window functions in FIR filter. It's absolutely unnecessary, because window functions can be tabulated, you can look them up. What needs to be picked up from this course is the fundamental understanding of how you use the window functions. What do the window functions do? Why do you need windowing in FIR filter design? These are the concepts that you should carry, and you should be able to use the window functions effectively with the different compromises. So some windows, like the Blackman window, are going to give you very low side lobes, but they are going to expand the transition band. The main lobe is going to expand. And others, like for example, if you use the Hun or Hamming window, then it would in some sense let some side lobes go through, but then it would reduce the transition band. Now in fact, in terms of least squared error, you might be interested in understanding that the rectangular window is optimal. So no windowing. In some sense, if you don't window, you are least squared optimal. That means you are making the best approximation in terms of squared error. But in terms of maximum error, so it depends on what criterion you want to apply when you are doing windowing. So what I'm trying to emphasize, so if one is trying to minimize the squared error, then one should not do windowing. One should simply let the samples go as they are for the interval of interest. If one is not interested in squared error minimization, rather one is interested in minimizing the maximum error, that's called the minimax criterion, then you should be using windows, you should suppress the side lobes. But then you have to be content with letting the main lobe expand. So, in some sense, FIR filter design by windows is a compromise between the main lobe width and side lobe area, or the side deviation, maximum deviation, right? Now, have we got an answer? So, it will be nice to hear from. So, is Narendra on the call? If Narendra is on the call, then he needs to tell us whether we have addressed his question about formulae. And if he can be more specific about what formulae he wants us to tell him about. So Manu, have we answered your question on the twiddle factor? If there are more questions, please put them on the chat. We are looking forward to more questions. More questions or more observations that we can respond to. Anyway, about the assignments, I think Aniket is looking at the assignments. He would definitely. I think maybe only in a couple of assignments there would be some errors.
Yeah,
right?
This assignment it's not really serious. I was just waiting for the week 12 if they have any corrections, and I'll just send all of them at once.
Right. So for the week 12, we'll send. This is in week 12, is it?
Yeah, this is the last week.
Last
week. I thought I'll just send all of them.
Yeah. So we'll send all the corrections at once. That's what Aniket tells me. So I mean, we also would definitely want the corrections to be made, right? When we notice them, and we'll do our best to, incorporate the corrections even in the evaluation. But I mean, finally, we are all human, I guess. Now, do we have any other questions? Do we have any other? No, we have no other, so we are waiting for more questions. More questions or something that we can respond to. How many people are there? 3. One in the call now, can you find out? See, that we got it. 3 watching now. So do we have more questions or do we have more queries? Or anything that you would like us to talk about? Well, it seems that I don't think there are any more questions. There are 4. Okay, there are 4 watching now. So any questions, anything that you would like us to respond to, please? Okay, doesn't look like there are any more questions. So perhaps we should then conclude the session here. We can conclude the session if nobody has any questions or any other comments. Yeah. Okay. Then we can conclude the session if there are no other further comments. We wish you the very best for your examination. Yeah. We'll close the session.